All right, section 4 is a lot like section 3 in that it's going to show us a different way of representing things that we've already seen. Polar coordinates actually something you guys have a lot of experience from, mainly from Algebra 2, but also I believe we did some of it in geometry. We also do it in trig here. But I actually prefer the Algebra 2 book's way of representing things. We'll go over some of the differences with this book. But just as a reminder, if I had something in rectangular that was the point, say 2, 3. So it's over 2 and up 3. And that's where the point is. In polar, I want to have a direction and a magnitude. So I would do something like do the Pythagorean theorem to figure out what the magnitude is. And so that's going to end up being the square root of 13. And then I would use inverse tangent, because I'd say the tangent of this angle here is equal to opposite over adjacent. And so when I do that inverse tangent, I would get that theta is approximately 56.3099 degrees. Of course, you could do it in radians, but the point 2, 3 that's rectangular, its polar counterpart is going to be square root of 13 and 56.3099 degrees. Now this is the notation that the Saxon books use. Our book doesn't use that quite as much. In fact, they will just put a lot of times polar, like point, and they'll just put square root of 13 comma 56.309 degrees, something like that. And you need to just know that that's polar. That's one of the reasons I don't like the pre-calc book and how it represents things as well. But of course, there's going to need to be the opportunity to both go from rectangular to polar and also from polar to rectangular. So if I have something where I say the polar coordinates are 5 and I'm going 110 degrees, well, it's very easy to find the x by doing 5 times the cosine of 110 degrees, and y is 5 times the sine of 110 degrees. And that's because if I had set this up, going 110 degrees is going like this, and going out 5. And so if I have the x and the y here, by just doing it this way, it takes care of whether I'm going to be positive or negative. But in truth, I would be saying cosine is adjacent over hypotenuse. That's where the x comes in. And sine is opposite over hypotenuse. That's why sine and y. I always think alphabetically. C comes before s, x comes before y. So these things haven't changed. I really like how that's done in Algebra 2 and whatnot. The way that our book writes the formulas, you're going to see, not too much different. They say x equals r cosine theta. That's what we just went over. Y equals r sine theta. R squared is equal to x squared plus y squared. That was something that we wouldn't have talked about in Algebra 2 because you wouldn't have known those trig identities. But if I do x squared plus y squared, what's that going to mean? It's going to be r cosine theta squared plus r sine theta squared. And if I factor out an r squared from both of those, I get x squared plus y squared equals r squared, and then cosine squared theta plus sine squared theta, which of course we learned last chapter that's equal to 1 by one of the Pythagorean identities. So we just end up with x squared plus y squared equals r squared. And the other thing that we already talked about was the tangent of theta is equal to y over x. And of course that's how we just figured out the angle if we had something in rectangular by doing an inverse tangent of y over x. So in general, the big things that I would ask you to do is to go back and forth between these two. I am going to show you a calculator example of how you can graph things in polar. And again, you can do some fun things, and section 5 of this chapter will show you some of those fun things. But just some of the keys are just converting from one to the other. Now, I want to do one more example, and then I'll have a little calculator video for you also. Look at the last example in your book on page 538. It says, radar detects 2 airplanes in the same altitude. Their polar coordinates are 8 miles at 110 degrees and 5 miles at 15 degrees. So if I'm the radar center and I say over here at 110 degrees I'm out 8 miles, there's one plane there, and 15 degrees I'm at 5 miles. I'm going to have something that looks kind of like that. I may want to know, hey, how far apart are those two airplanes? And so what's nice is this is going to be a good application of the law of cosines, because really I'm looking for this third side here, find what that distance is when I know this side is 8, this side is 5, and I can figure out that the angle in between them is going to be 95 degrees, because from 15 to 110. So using the law of cosines, I could say that d squared equals a squared plus b squared minus 2 times a times b times the cosine of that c, or the d. And so if I plug that all into my calculator and take the square root, I end up getting something approximately 9.8 miles. So yes, I skipped through all the hard math, just put that in the calculator. So it's something that's useful when I have things in rectangular, or excuse me, in polar. I don't have to necessarily go back to rectangular, because I can still use some of the information that I've figured out in previous chapters.